So in this video, we're going to recap linearization. So linearization is just a process which is used to linearize some complicated functions. So in other words, to make them a little bit simpler. And what we're going to find is that in the context of this control stuff, we're going to end up with equations that can be easily Laplace transformed and then turned into transfer functions. So that's the kind of incentive of applying this method. So let's just talk about what a linear equation looks like and what a nonlinear equation looks like to know when this would need to be applied. So if I had kind of these normal equations that we've been working with, I'm just going to make one up off the top of my head like this. So x double dot plus 4x dot plus 5x. This one here is a linear equation, and it's going to be quite easy to Laplace transform this. So all we're looking for to identify whether it's linear is basically that we have like constants out the front of our different terms, and that we've got x double dot and x dot here, which is fine, but for the x term in particular, it needs to be an x to the power of 1, okay? Anything else, it's not going to be linear. So let's give a couple of other examples. Let's say I had x double dot plus 4x dot plus, let's say I now have 5x squared, okay, is equal to 0. So this now represents a nonlinear function because we haven't got x to the power of 1. In fact, we've got x squared. Another example, let's say that we had in here, let's say we had 5 sine x equals 0. So this isn't an x to the power of 1 anymore, right? It's like a sine of x, okay? So again, this part here is not a linear part of the equation. One last example, if we had like x double dot plus, say, 4x x dot plus 5x equals 0, again, this one does not represent a linear equation because we have an x multiplied by an x dot, okay? So this isn't anymore a constant out the front of our differential part there. Okay, so all of these are examples of where you would need to apply your linearization technique in order to turn it back into something that looked like this top equation here, where you just have constants out the front of your terms and a power of 1 for the x. So how we do this is we actually apply Taylor series. So let me just write out the equation for Taylor series. So at a value of x, okay, so you need to pick a value that you're going to apply this Taylor series around, and I'm going to pick a. We can apply the equation f of x is equal to f of a, plus then we have this summation thing where we go from n equals 1 to infinity, and then we take the derivative to the nth time, divided by this is n factorial, and then x minus a to the power of n. Okay, so n just keeps increasing, so start at n equals 1 and increase up to infinity. So that's where it's directly equal. However, it's impractical to apply this to infinite n. So what we tend to do is say, okay, we can approximate this by just kind of cutting it off after a certain number of terms. So say we take the first one, which is n is equal to 1. This is going to be f dash at x equals a, divided by n, which is 1, so 1 factorial, and then x minus a to the power of 1. Plus, okay, let's say we take n equals 2. It's going to be f double dash of a, so the second derivative at a. This becomes 2 factorial x minus a to the power of 2, and so on. We can keep going with as many as we want. Now, for linearization, what we are actually going to do is say, okay, we're going to stop at n equals 1. So that's this term here. And we're going to set all of the higher order terms, so that's HOT, to be equal to 0. Okay, and what that means is we end up with a fairly simple equation, which is going to approximate the function that we're looking at. So we can set this function to whatever we need it to be. So in these kinds of examples that I had here, you know, f of x could be 5x squared, it could be 5 sine x, or this one we'll deal with a bit later, but the 4x x dot as well would work in this kind of situation. So what I'm just going to quickly do is rewrite this a little bit differently. So we're going to say that f of x is approximately equal to, I'm going to call this x0. And the reason I'm doing this is just because in a moment we're going to introduce more variables. So let me pop out the side here. We're looking at x0 for this version of it. Alright, so that's where we're expanding around. And then this I can rewrite, instead of f dash of a, I'm going to write this as the derivative of f with respect to x, our variable, at a. Sorry, we changed over a to be x0. And then this becomes x minus x0 to the power of 1. Right, so this is like our linearization equation when we just have the one independent variable that we're tracking. So if we were to draw this, say we have our like x, and this is f of x, and this was the original function that we were looking at, all right? So we needed to pick a value to expand around. So I initially called it a, but now let's call it xo. Okay, so that's our point of interest. What we're doing is at this point of interest on our graph, we're fitting a straight line to it through that point, like a tangent line. Okay, and we're going to treat this as where the variable moves over x, rather than this original function, which was nonlinear. Right, so this is our linearized f of x that falls out of this equation. So an important thing to note here is that you can see this approximation is only going to be accurate in the region of this x0 point of interest. Okay, as soon as we move far away from it, you know, we can extend this as far as necessary, but as soon as we get very far away from it, it's not particularly accurate anymore. Okay, this isn't such a problem for control situations, because what we're going to look at in a moment is picking a point of interest around the equilibrium of the system and then using that to fit the Taylor series. And what we know is that it's a control system. It shouldn't move too far away from the equilibrium position. Alright, so the other thing to note is that we can expand this to have more variables than just the one in terms of f of x. So let's expand it. Let's say that we have, well, I'll include the x one. So x equals x0. Let's say we're also interested in y equals y0 and z equals z0. Okay, and we have some function which is of x, y, and z. Okay, so we're going to fit this with the Taylor series around x0, y0, and z0. So it kind of follows the same pattern as what we've got here. So we say that our function x, y, z is approximately equal to, and here we replace it with, instead of x0 on its own, it's going to be all three of our variables in here, so the function at each of our points of interest all put together, plus then we saw we had a derivative term here of our function with respect to x evaluated at our point of interest. Okay, so we're going to follow this same pattern, except we're going to have a derivative term for every single one of our variables in the equation. So if we start with x, this time it's going to end up being a partial derivative because we have more than one variable, independent variable. Okay, so df on dx, and we're going to evaluate this at our point of interest, which is where all these three happen. So x0, y0, and z0. And then we saw here that we multiply it by x minus x0. So we're going to follow the same pattern here, x minus x0. So now we just need to repeat this for our other terms in the equation. So plus, so we then need to take the partial derivative of our function with respect to the second variable, which is y. We evaluate it at the same point of interest, x0, y0, z0. And then we multiply by the difference between y and y0. We have one more variable, so we're going to do this one more time. So partial derivative of the function with respect to z, evaluated at x0, y0, z0, and then multiplied by the difference between z and z0. And you can do this for as many variables as you need to. So the last little bit here is just the application of this process to our control problems. So we've got two kind of steps that we need to go through. So step one in doing this is that we need to identify or find our equilibrium position. right, or values, same diff. So we need to identify these. Remember that equilibrium, this is the same as like steady state. So at steady state or at equilibrium, all of our time derivatives are going to be equal to 0, and then potentially we need to find some other variables and what they would be in our steady state. So that's the first one. And then the second step that we need to do is apply the Taylor series process that I just wrote about above, about the equilibrium position or steady state position. So this provides you with an equation that has been linearized. Sometimes there is a kind of step 3 that you can go through, and this is in order to convert your equation into a transfer function by applying your Laplace transforms. And when we do this, what we end up needing to do is changing over our variable x. So if we have x dash, okay, what this is representing is the deviation from steady state or equilibrium. Okay, x is just the variable that we were originally tracking, and this one here, x with a bar over the top, this is representing the equilibrium value of x. So what we end up doing is swapping over, and instead of writing our equation in terms of x, we write it in terms of this deviation variable x dash. And what you find is that x minus this x bar back up in our Taylor series expansion, I'll go to the simpler one, which is where we just have the one variable. It basically ends up being this part here. So this is x, and x0 was our point of interest. Okay, so for these control problems, our point of interest becomes the equilibrium. So essentially, the x minus x0 is the same as this x minus x bar, so we can just directly replace it with this x dash variable instead. And when you write it in terms of this x dash variable, you end up with a linear equation that you can then apply Laplace transforms to make it into a transfer function, and then just apply your regular rules, techniques, concepts, whatever, as normal. So I'm going to leave this video here, and I'm going to do a couple of examples to hopefully demonstrate this process to you for control problems, and hopefully it will become a little bit more clear how we can follow through these steps in order to achieve a transfer function. So that's all there is for this video, and I will see you in another one.